right. Thank you. Yeah, so I'm talking about a subject that is not really one that most reputable astronomers will tell you about. No, you'll never go up to somebody and ask them, "Would you get your PhD in rogue planets?" That's just not really something people legitimately study. But we actually we're seeing things out there in space that kind of look like rogue planets. I'll tell you what we've been learning about them. Really, though, when I think of the term rogue planets, it's something more from science fiction. This is a movie I liked when I was a kid. I'm not actually this old. I just watched old movies when I was a kid. And so I think of some sort of planet hurtling toward the Earth. Of course, it's always on some collision course with us. We're like the unluckiest planet in the solar system. And it's going to come and destroy us. But the things I'm going to be telling you about today are at a very safe distance. They're not hurtling towards us that we know of. They're just out there floating in space, and they're just sort of interesting things to contemplate. So they're not going to be rocky worlds like you might like to think of, something you could stand on with maybe an atmosphere or something. They're going to be big, fat, bloated, gaseous, giant planets. Think Jupiter, or maybe several times the mass of Jupiter. And so they're not all the sort of things you often see in science fiction. They're way out of the solar system. They're gas giant-like. And the reason we see them is because they actually emit light in the infrared for us to detect. They're warm, and so they're glowing, and so they emit infrared light. So I think we're nowadays pretty used to the concept of infrared light because there's a proliferation of infrared cameras out there. So this is the one on the picture on the left is a picture a friend of mine took of me at a conference with the infrared camera they could plug into their iPhone. And then on the right is a picture of Jupiter in the infrared. And the main thing to note is that there are bright regions and dark regions. So on Jupiter, the dark regions are clouds that block our view of the deep, hot gas, and so we're only seeing the higher, colder gas. On humans, of course, the cheeks are cooler, so they're darker. Different parts of my skin are warmer than others. And I got a beard in this picture, so like the hair is cooler. I probably just like lifted my arm so you could see my armpit be glowing or something. And so it's this sort of infrared technology that's been growing over the last couple decades that has really sort of opened up the universe to us to be able to see things that are just glowing in the infrared. And so you occasionally nowadays see headlines talking about, with photos and even videos, talking about planets that are out there on their own in the galaxy with no star to host them. And so what is it makes astronomers decide that something is actually a planet and not something else? There are basically two things that we look for, and I'll go into much more detail about this. The two things we look for are things that are very cool and young. So things that we think we're seeing early on while they're still glowing hotter. When they get older, they're fainter. The other thing is just very, 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 very cold. So something that's just like so cold that it can't possibly be something higher mass than a planetary mass thing. So what's going on here? So I have to introduce you to brown dwarfs. If you're not familiar with brown dwarfs, they're things that sit between stars and planets. They share one property with planets, which is that they do not have nuclear fusion in their core. And so planets and brown dwarfs both just get fainter with time. And so that's what I'm showing you here, just a sort of cartoon picture of this, brightness versus age on the x-axis. This blue curve up here on the right is a cartoon of a star. A star initially contracts, but fusion helps it establish an equilibrium, and so it maintains a stable equilibrium where it just shines for about the same brightness for billions of years. Brown dwarfs and planets don't do this. And so they simply get fainter with time. So the tricky part of trying to say if something is a planet or a brown dwarf, something much, much more massive, brown dwarfs can be up to 75 times the mass of Jupiter, something that we would really think of as being more like a star, and we see lots of them. We see them forming like stars in star-forming regions. We see brown dwarfs that are that massive with disks and all that sort of thing. How do we distinguish between a planet and a brown dwarf? Well, you might think you could just go and see, well, if it's faint, it's a planet, but in fact, you run into this problem where you measure the brightness of something. It's only if it's that brightness and it's young, then yes, it is a planet because the lower mass things start with less energy, and so and more massive things start with more energy. So to get to that brightness, a brown dwarf would have to be older, and so you might be looking at something that is an older brown dwarf. Or you might even be, in some cases, if you're really unlucky, you might actually be looking at just a really low-mass star that happens to be faint because it's on the very tail end of the stars that exist. So for this reason, this is what I mean by we have to look for things that are both cool and young. So you have to be faint and also young in order to be classified as a potential planetary mass thing. And the other possibility is, since we live in a universe that has a finite lifetime, the universe has been around for 13 point something billion years, ask the cosmologists what the age is this week, but that means that there's a finite limit on how long these things have, the amount of time they've had to cool. So if you find something that's really cold, then you're actually definitely looking at something that is, there's an upper limit on the mass just from the age of the universe. Okay, so I'm going to first talk about this first case, though, this cooler and younger thing. So there's two parts of this, right? The two parts are brightness and age. So first, let's do brightness. Brightness is a classic problem. If you look up in the sky tonight, you see a star, you're not going to be able to tell me, unless you know the star, you're not going to be able to tell me if it's not a bright star that's really far away or if it's a faint star that's closer to us. It could be a giant star that's very distant or a nearby dwarf star. So to figure out objects' brightnesses, what we have to do is develop some sort of 3D technique where we can see the distance and figure out the distance of these stars. We see not just the position, but also how far away it is. And so this is something it's been known about for a long time. It wasn't measured until the 1800s. It's parallax, stellar parallax. And so we use the fact that the Earth orbits the sun, and it moves by 2 astronomical units every year. Every 6 months, it moves. And so you can take an image of a star in June, you can take an image of a star in December, and it will appear to move with respect to distant background stars. And so this is basically, the reason I use the 3D glasses is basically the same sort of technique that's used to make 3D movies, right? You set up 2 cameras at 2 different places, and then you shoot the same scene, and then you get this parallax effect that allows the actors to pop out against the background. So that's effectively what we're doing. We're just doing it over years instead of doing it all in one space. So this allows us to measure the brightness. Now that establishes how cool something is or bright or faint it is. So now we need to know the age. This is probably the trickiest thing to do in astronomy, measuring ages, but we are given a little bit of luck, which is that we don't have to go and chase down birth certificates for every single star. Stars are actually born very differently from humans. I kind of like to think of it as the baby spiders from the end of Charlotte's Web. These baby spiders all sprung out all at once, and there's some wind blowing, and so they get some characteristic velocity in the motion. So young stars are the same way. They form all out of one cloud of gas, and that cloud of gas has some motion. And so stars will be, for a little while at least, not for their whole lifetimes. The sun, we don't know what stars the sun formed with, but for very early times, we can actually see stars that belong as a group that all form together out of one brood. And so I have a couple movies to show this. They might take a second to load. This is actual data. On the left is going to be a movie of what you normally think of, space, 3-dimensional space. And then on the right is velocity space or kinematic space. Basically, what is their vector of motion? So basically telling you the angle that they're moving at as they're orbiting the galaxy. And so the colored dots here are individual stars, and then the same color is one group of stars that was all born together. And so the reason why we think they're born together, of course, is this data. It's groupings that are clustered together in space in both of these dimensions. So it's really a 6-dimensional space. We're breaking it down into 2 3D dimensions. And so this is how we can age date stars. We can figure out where they are in space, which I've already told you how we can locate them in 3-dimensional space using our 3D glasses of parallax. So then the only thing is to measure their motion. And so that is actually pretty easy. You just come back and you just observe a star repeatedly over time, and you'll see it move. So I'm about to show you, so here's a stack of 2 images that were taken at different times. One is in orange, the other one's in blue, and most of the stars in this image are not moving, so they just look white. But you can see there's something right in the middle here that's moved. This is an extreme example of something that moves very fast. But all stars have some small amount of motion, and we can measure this. So we can actually use the same data that we use to measure the parallax to actually measure these things very precisely. So we're still missing one dimension. That last dimension, of course, is the motion in and out of the image here, and that's redshift or the Doppler effect. The redshifts of stars near us are very small compared to the redshifts of distant galaxies that you may have heard about at other talks, but it's the same technique, same basic idea. So we can use the motions, the positions to sort of fingerprint stars, put them in groups, and then we now have the ability to measure brightness, and we have the ability to measure age. And I'm going to skip over a couple slides here and get to the more interesting thing, which is one of the most famous groups of stars is the Beta Pictoris family. It's 23 million years old. There's a lot of papers, people talk about it a lot, people write about it a lot. It's kind of like the Kardashians of the young families of stars in the solar neighborhood. It's an imperfect analogy because they were born all at the same time. It'd be like if the Kardashians all sprung out of one person all at once. Maybe that's kind of scary. Okay, but so the image on the left is Beta Pictoris b, the eponymous member of the group. It's a massive star. It's really famous because it has this giant disk of debris. We think this is due to planetesimals grinding up and creating dust. And this was known since I think the 80s. And only recently, though, have we found this guy. This is a 13 Jupiter mass planet orbiting the star. And in fact, we have a lot of data of it moving back and forth and back and forth. So it's orbiting a star, and it's planet. Last year was announced what's perhaps the lowest mass directly imaged planet that we have. Maybe it's only 2 times as massive as Jupiter. It's orbiting a star called 51 Erie. The starlight has been subtracted here, so you can sort of vaguely see it there. And then the image in the upper right is another member of this family, same age, and it's actually a little bit fainter than Beta Pic B, but it's brighter than this thing. It's fainter than this planet, brighter than that planet. It sits in the middle. We think it's about 8 Jupiter masses, but it has no star. There's no star next to it, and so this is sort of the black sheep of the Beta Pictoris family. So it was first identified because it's just extremely red. In fact, it might be one of the reddest planets that we know about through direct imaging. And we think the redness has to do with really thick dust clouds, so maybe it's just the cloudiest planet. This is one of the few sort of free-floating things that has been confirmed by this Doppler effect. That was a recent thing. And more developments recently since we found it. And by the way, this is where the Ultracool Tool comes in. The tools I developed allowed us to basically measure the parallax for this thing and the proper motion, and actually fingerprint it and put it in the group. So that was my contribution. Recently, it's been shown that it actually varies in brightness by about 10%. So 10% may not seem huge, but to put it in context, the Great Red Spot on Jupiter covers only about 1% of the surface. So we think this brightness variations is some sort of surface feature that's rotating in and out of view. And so the implications is that maybe it's some sort of, if it's really cloudy, maybe it's some sort of storm complex that's 10 times bigger than the Great Red Spot. We're really not sure what's going on yet. Another interesting attribute of this is that it has a song on YouTube that's been dedicated to it. It's a sad song because it's a lonely planet, and I don't know that any other planets have their own songs. And more importantly for tonight, in fact I see it over there, there is a poster that was made by the NASA Exoplanet Science Institute. They have made a series of posters called the fictitious Exoplanet Travel Bureau, inviting you to visit various planets and people have discovered. So they did one for this one because it kind of has lots of the attributes that we have seen around directly imaged planets, but it just doesn't have a star. So the tongue-in-cheek thing here is that, of course, if you don't have a star, then it's always nighttime. So if you're really interested in just like partying all night, this is where you should go. There's some megastructures here that I imagine are very luxurious, and so you show up in your tuxedo-shaped spacesuit and go party. So check those out. All right, so I'm talking about what we found, how we find them. The interesting thing is sort of where do they come from? What is it? They're really great objects we can study. We can learn about how planetary atmospheres work and things like that without the glare of a bright star. But really would like to know their origins. And so there's basically 2 possible stories for this. One is that they were, in fact, formed like a planet and were ejected. So when a star and a disk love each other very much, they make a lot of planets. And sometimes, and those planets are orbiting each other, they sort of nudge each other around with their gravity. And sometimes they play a little too rough, maybe, and one of them just gets kicked out of the system into the void of space. It's pretty dire consequences. There's some people, I don't know how reputable these models are. Some people actually think that this happened in our own solar system to explain what we see about the planet orbits and the Kuiper belt and the asteroid belt, that you had to start with 5 planets, have some sort of gravitational interaction that kicked one of them out, and then you end up with 4 planets. I'm not saying this happened. I'm just saying this is the sort of thing, this is a serious possibility that could happen not only here, but around other stars as well. Now, the other scenario is sort of akin to spontaneous generation. If you think of planets as being born from people, ancients actually thought ancients understood that humans came from humans, and you had to have that happening. But they thought like fleas and aphids and things came from just inanimate matter, and so that's sort of the analogy here. Astrophysically, what this means is, planets are really just part of this vast landscape of stars. And really, they form just like stars, but way down in the bottom right corner of this sort of classic Hertzsprung-Russell diagram that you've probably seen at some point. So where they come from, it really kind of boils down to these 2 questions. One is, how often do planets get kicked away from their parent star? And the other question is, what is the lowest mass planet that we can just form on its own directly from the gas cloud itself? The first question is completely, I don't think we have any data. I can't even think of an experiment that we could do with existing telescopes to really test that. It might happen. The other one, we don't know the answer. I can't tell you. We don't know. But I will say that I think we have some intriguing leads, and then future telescopes like the James Webb Space Telescope that is going to be a successor to Hubble might be able to answer. So what is this intriguing lead? There is a star that was found. Sorry. Okay, missing a slide. There's a star that was found very recently in a all-sky survey in the thermal infrared. The first time we'd ever gone this deep at the thermal infrared wavelengths, called WISE 0855-0714. So we just barely detected it, but it happens to sit really close to us, 7 light years away. In fact, if you bundle up stars to the Alpha Centauri Proxima Centauri system, this other brown dwarf system, Barnard star, and then this, so it's the 4th closest system to us, and we didn't even know about it until a couple of years ago, until we did this whole infrared survey. It's so cold, it's actually the surface of this planetary mass thing is colder than the surface of the Earth. And so this meets the criterion that I mentioned earlier, that it's so cold that at the age of the universe, it would actually have to be planetary mass. And to me, what's really intriguing is that we found it right at the edge limits, the limits of our survey, and it's right next door. So does that mean that there's 10 more living right outside where we couldn't detect them? Maybe there's some huge swarm of these things, and we're only detecting the very tip of this sort of iceberg of planets. And so I think that's something that we'll learn a lot more about in the future, and thanks.
All right, we have time for some questions for the Ultracool Tool. Let's see. Right here.
Why is it that you believe these have to be gas giants and there's no chance that they can be a rock planet?
So there. Okay, so the question is, why do they have to be gas giants? Why can't they be rocky? And the answer is that they're putting out so much energy, they're putting out so much light that, there's no real way for a rocky planet to do that. So the brightness of something is related to its temperature and then just how the size of the surface. So the bigger the surface is, it's the more light it puts out. The temperature, of course, is something. If you've seen an electric stove top thing, when things get hotter, they get brighter. So it's just that calculation of hotness versus radius, so they have to be big.
Right down here.
How many of these rogue planets have you discovered?
So that's a good question. So I was looking on Wikipedia to make sure I wasn't like forgetting something, and And the one I showed you is I think the best candidate, or the best case we have. It means confirmed as a member of Beta Pictoris and blah blah blah. But if you want to call it a rogue planet, that's the best one. That I would say is most planety. Other ones have been claimed. So some of the article clippings I've shown you, like we didn't have the full fingerprint yet, and so we went back and got better data, and some of them have gone away, and we haven't published all of that yet because it's always better to publish discovery than whoops, we were wrong. So there's really just like a couple. I would say this object YSO855, PSOJ318, and then in star-forming regions there's some things that look very young, but they're very far away and we don't have as much information on them.
Do we know where WISE is going?
So the question is, do we know where this object that's so close to us is going? And one thing I realized when I was preparing this talk is I don't think anybody's measured the Doppler effect for this thing, so in principle it could be hurtling towards us. It's pretty unlikely.
Very good to know. All right, one more question for Ultracool Tool. All right, there we go.
So are there enough of these out there to potentially be machos that could be dark matter?
Okay, so the question is, could these be machos and dark matter? So don't remember, Jeff, do you know what macho, can you remind me what macho stands for?
Massive compact halo object.
Thank you, okay. So brown dwarfs are compact, or planetary mass things are compact. They're somewhat massive. They're not as massive as brown dwarfs are, but the earlier work on gravitational microlensing surveys did not detect swarms of massive things. They have detected, there's a whole, that's a kind of a separate talk, they have detected some intriguing bump in their data that looks like it might be due to some planets. Those planets could be orbiting stars, we don't really know. But basically, we already know from microlensing surveys that the galaxy isn't teeming with vast numbers of these things.
Cool. All right, let's thank Ultracool Tool one more time.